Hello everyone. Today we will study the cumulative distribution function. Cumulative distribution function, sometimes it's called a CDF. CDF represents the cumulative distribution function. First of all, let me introduce what it is. Let x be a random variable. The cumulative distribution function of x is defined as capital F of x. Capital F of x, this is lowercase x. Capital F of x is the probability that x is less or equal to x. This is lowercase x. This is capital X. Capital X represents a random variable x. So the CDF of x is defined as f of x equal to probability that x less or equal to x. Capital F represents the CDF, cumulative distribution function. Note, be very careful. CDF is not the same as PDF. CDF and PDF they are different. If x is a discrete random variable, if s is a discrete random variable, then lowercase of f represents its probability function. Lowercase f represents probability function. Lowercase f of x represents probability that x equal to x. For if x is a discrete random variable, f of x represents probability that x equal to x. That's the probability function. Capital F of x represents probability that x less or equal to x. This is the CDF. Capital F of x is probability that x less or equal to x. Now, if x is a continuous random variable, then lowercase f of x represents its probability density function. If x is continuous random variable, then lowercase f represents its probability density function. Be very, very careful. F of x is not the same as P of s equal to 0, P of s equal to x. For PDF, be very, very careful. F of x is not the same as probability that s equal to x. Because for PDF, probability that s equal to a constant, for any PDF, probability that s equal to a constant is always 0. For any continuous random variable, probability that s equal to a constant is always 0. So they are not the same. Because probability that s equal to x equal to 0 for all x. So be very careful. If s is discrete, the probability function f of x is probability that s equal to x. If s is a continuous random variable, then for the PDF, f of x is not the same as probability that s equal to x. because probability that s equal to x is always 0. And the CDF we define the same way. CDF is probability that x less or equal to x. So you can see that in both cases, it doesn't matter if s is discrete or continuous. Their CDF is exactly the same. F of x is probability that x less or equal to x. Their CDF is exactly the same, but the probability function and the probability function they define in different ways. Be very, very careful. Next, let's look at an example. Let x be a discrete random variable with probability function f of x, such that f of x equal to 0.2 if s is -1, f of x equal to 0.3 if s is 0, 0.1 if s is 3, 0.4 if s is 6. Part A. Evaluate each of the following expressions. Evaluate each of the following expressions. First expression, capital F of -2. How to evaluate capital F of -2? Capital F represents the CDF. Capital F always represents the CDF, the cumulative distribution function. Capital F of -2, by its definition, is probability that x less or equal to -2. Keep it in mind. Capital F of any x is probability that x less or equal to x. Capital F of x is probability that x less or equal to x. This x is a random variable. This x is a value in the parentheses. So f of -2 is probability that x less or equal to -2. If x is less or equal to -2, what's the support here? What's the support of this function? Support of x here is -1, 0, 3, and 6. Try to find the support first. Here, support for this random variable x is -1, 0, 3, and 6. Find the support first. Now, we want to find probability that x is less or equal to -2. None of them here is less or equal to -2. So this probability is 0. Next, what's capital F of -1.1? What's capital F of -1.1? By the definition of CDF, this is probability that x less or equal to -1.1. Capital F represents the CDF. We use this formula. CDF f of x is probability that x less or equal to x. So we're looking for probability that x less or equal to 1.1. Probability that x is less than or equal to -1.1. Here in the support, none of the values are less than -1.1. So this probability is 0. Next, what's f of -1? F of -1 represents probability that x less or equal to -1. F of -1, by its definition, that means probability that x less or equal to -1. When s is less than or equal to -1, in the support, the only value here is -1. Only -1 is here is less than or equal to -1. So not equal to lowercase f, f of -1. Only -1 is less than or equal to -1. So probability that x less or equal to -1 equal to probability equal to f of -1. This is lowercase f. This is lowercase f. The probability function f of -1. For f of -1, look at the function. When s is -1, f of x is 0.2. How about f of -0.1? How about f of -0.1? By definition, it means probability that x less or equal to -0.1. Probability that x is less than or equal to -0.1. Look at the support here. In the support, only -1 is less than -0.1. Only -1 is less than -0.1. So we have f of -1, which is 0.2 here. Next, what's capital F of 0? What's f of 0? This f is a CDF, so by its definition, it means probability that x is less than or equal to 0. That's probability that x is less than or equal to 0. In the support, only -1 and 0. Only -1 and 0 satisfies that x is less or equal to 0. So we have f of -1 plus f of 0. f of -1 is 0.2. What's f of 0? f of 0 is 0.3. 0.2 plus 0.3 is 0.5. That's capital F of 0. Now, how about capital F of 2.9? How about capital F of 2.9? That's probability that x less or equal to 2.9 by definition of the CDF. By definition of CDF, that's probability that x less than or equal to 2.9. If x is less than or equal to 2.9, in the support, all we have is -1 and 0. If x is less than or equal to 2.9, all we have in the support is -1 and 0. That's f of -1 plus f of 0. Then f of -1 is 0.2. f of 0 is 0.3. Adding up, we get 0.5. What's f of 3? What's f of 3? f of 3, by definition, is probability that x less or equal to 3. By its definition, it means probability that x is less than or equal to 3. In the support, -1, 0, and 3 satisfy the condition x less than or equal to 3. So we have f of -1 plus f of 0 plus f of 3. f of -1 is 0.2. f of 0 is 0.3. f of 3 is 0.1. If we add them up, we get 0.6. If we add them up, we get 0.6. That's f of 3. Next, how about f of 5.9? f of 5.9 is probability that x less or equal to 5.9 by definition of CDF. So look at support. Which x here is less than, which number is less than 5.9? All we have is -1, 0, and 3. So we have f of -1 plus f of 0 plus f of 3, which equal to 0.2 plus 0.3 plus 0.1. Together, it's 0.6. That's f of 5.9. How about f of 6? What about f of 6? f of 6 is probability that x less or equal to 6. f of 6 is probability that x less or equal to 6. In the support, -1, 0, 3, 6, they are all less than or equal to 6. So we have probability that f of -1 plus f of 0 plus f of 3 plus f of 6. Together we have 0.2 plus 0.3 plus 0.1 plus 0.4. Adding up, we get 1. So f of 6 is 1. Next, how about f of 100? How about f of 100? By definition of CDF, that's a probability that x less or equal to 100. In the support, which x is less than 100? Here we can see that all x here is less than 100. So we have f of -1 plus f of 0 plus f of 3 plus f of 6, which is 0.2 plus 0.3 plus 0.1 plus 0.4. Together, we get 1. Part B. Find the CDF of x. Find the cumulative distribution function of x. Find the CDF of x. Usually when we try to find a CTF, if possible, let's try to draw the graph first. When we try to find a CTF, if possible, let's find a graph first. Then find a function based on a graph is much easier. Let's draw the graph first. Here, f of negative 2 is 0. F of negative 2 is 0, is here. F of negative 1.1 stays at 0. And when we reach f of negative 1, the function jumps up to 0.2. For f of negative 0.1, the function stays at 0 here, stay at 0.2. Then when the function reaches 0, for f of 0, when the function on x reaches 0, when x reaches 0, the function jumps up to 0.5. Then the function stays at 0.5 until 2.9, 1, 2, 3, until it's very, very close to 3. Then when you reach 3, for f of 3, it jumps up to 0.6. Before 3, at 2.9, it stays at 0.5. When you reach 3, when x reaches 3, the CTF jumps up to 0.6. Then it stays at 0.6 until 5.9. 4, 5, 6, 5.9. Then when x reaches 6, it jumps up to 1. When x reaches 6, f of x jumps up to 1. And then it stays at 1 for all x. It stays at 1 for all x. When x reaches 100, it's still 1. It stays at 1 for all x. Now, in the beginning, we know that f of negative 2 is 0. How about f of negative 3? F of negative 3 is probability that x less or equal to negative 3. In the support, none of the x is less than negative 3, so the probability is 0. Same thing for negative 4, and negative 6. F of x is always 0. So on the left side, it stays at 0. On the right side, it stays at 1. On the left side, it stays at 0. Now, when a function gets very, very close to negative 1, no matter how close it is, it stays at 0. When a function gets very, very close to negative 1, say we have negative 1.1, negative 1.00001. What's f of negative 1.00001? That's the probability that x less or equal to negative 1.0001. In the support, none of the numbers is less than negative 1.0001. In the support, none of the numbers is less than negative 1.0001. So this probability is 0. No matter how close it is to negative 1, probability is always 0. But when the function reaches negative 1, when x reaches negative 1, it jumps up to 0.2. Then stays at 0.2 until 0, it jumps up to 0.5. But before it reaches 0, if we have negative 0.0001, before it reaches 0, if we have negative 0.0001, f of negative 0.001 is probability that x less or equal to negative 0.0001. Look at support here. The only x which is less than negative 0.0001 is negative 1. That's f of negative 1. f of -1 is 0.2. So no matter how close it is, no matter how close to 0, it stays at 0.2. No matter how close to 0, f of x stays at 0.2. Then when you reach 0, when x reaches 0, f of 0 is 0.5. So at 0, it jumps up to 0.5. Then stays at 0.5. Stays at 0.5 until it reaches 3. Stays at 0.5 until it reaches 3. No matter how close to 3, it stays at 0.5. f of x stays at 0.5. No matter how close x is to number 3, f of x stays at 0.5. So no matter how close it is, even though we have f of 2.9999, no matter how close it is, let's probability x less or equal to 2.9999. In the support, the only x value that's less than 2.9999 is -1 and 0. So we have f of -1 plus f of 0, which is 0.5. So no matter how close x, no matter how close it is, no matter how close x to 3, f of x stays at 0.5. But when x reaches 3, f of x jumps up to 0.6. And similarly, no matter how close the function to 6, at 6 it jumps up to 1. But before x reaches 6, no matter how close x is to 6, before x reaches 6, no matter how close it is, even though we have 5.99999, let's probability that x less or equal to 5.9999. In the support, the only x less than 5.999 is -1, 0, and 3. So the f of -1 plus f of 0 plus f of 3, I get 0.6. So before x reaches 6, no matter how close it is, no matter how close to 6, it stays at 0.6. And when x reaches 6, f of x jump up to 1. When x reaches 6, f of x jump up to 1. And then it stays at 1. It stayed at 1 for all x. It stayed at 1 for all x. So that's the graph for the CDF. That's the graph of the CDF of x. Now how do we find a function? That's the graph. That's not what we want. We want to find a function. So for the CDF, the cumulative distribution function, we want a function. We don't want a graph. We want a function. How do we find a function here? This graph represents the CDF. How do we find a function? First of all, this is a piecewise function. It's first of all 0 if x is less than -1. If x is less than -1, f of x is 0. Then it's 0.2. It's 0.2 if x is between -1 and 0. Including -1, not 0. It's 0.2 if x is between -1 and 0. Including -1, but not 0. That's when x is between, when f of x is 0.2. Then f of x could be 0.5. When s is between 0 and 3, f of x is 0.5. And here x is between 0 and 3, including 0, but not 3. Then next, f of x could be 0.6. F of x could be 0.6, when s is between 3 and 6, including 3, but not 6. Including 3, but not 6. And finally, f of x equal to 1. Finally, f of x equal to 1 if s is greater than or equal to 6. If s is greater than or equal to 6. This is the CDF. This is the CDF of the random variable x. Here we found the CDF based on the PDF, the probability function. We find CDF based on the probability function. Next example, let x be a discrete random variable, and x has a binomial distribution with n equal to 4, p equal to 1/3. For binomial distribution, first number represents n, second number represents p. Find its CDF. CDF means the cumulative distribution function. So we try to find its CDF. First step, let's try to find the probability function first. Find the probability function for x first. Since x is a binomial distribution with n equal to 4, p equal to 1/3, the probability function for binomial distribution is f of x, n choose x, p to the power of x, 1 minus p to the power of m minus x. If we plug in n, plug in p, we have 4 choose x times 1/3 to the power of x. 1 minus 1/3 is 2/3 to the power of m minus x, n is 4. That's the probability function. That's the probability function of x. Next, we try to find the support of x. Since x has a binomial distribution, the support is the set of integers from 0 to n. Support of x is integers from 0 to n. Here n is 4. So the support is integers 0, 1, 2, 3, 4. Next, we plug in each value in the support into the probability function. We plug in each value in the support into the probability function. Try to find f of 0, f of 1, f of 2, f of 3, and f of 4. For f of 0, we plug in 0 for x. We get 4 choose 0. 1/3 to the power of 0. 2/3 to the power of 4. That's 1. That's 1. That's 16 over 27. 16 over 81. F of 1, we plug in 1 for x. That's 4 choose 1. 1/3 to the power of 1. 2/3 to the power of 3. Together, that's 81 on the bottom. 2 to the power of 3 is a. 4 choose 1 is 4. 4 times a is 32. Next, for f of 2, plug in 2 for x. Plug in 2 for each x. 4 choose 2. 1/3 to the power of 2. 2/3 to the power of 2. Denominator is 81. 4 choose 2 is 6. 2 squared is 4. 6 times 4 is 24. Next, f of 3. Plug in 3 for each x. That's 4 choose 3. 1/3 to the power of 3. 2/3 to the power of 1. 4 choose 3 is 4. 2 to the power of 1 is 2. 4 times 2 is a. I get a over 81. F of 4. Plug in 4 for x. We get 4 choose 4. 1/3 to the power of 4. 2/3 to the power of 0. 4 choose 4 is 1. So I get 1 over 81. Next, based on this information here, try to find a CDF. In order to find a CDF, let's find its graph first. In order to find a CDF, let's find its graph first. Its labeled axis 10 over 81, 20 over 81, 30 over 81, 40 over 81, 50 over 81, 60 over 81, 70 over 81, 80 over 81. The last point here is 81 over 81, which is 1. Let's label the x-axis 0, 1, 2, 3, 4. 5, 6. Here, f of 0 is 16 over 81. That's the smallest x value. 0 is the smallest x value. That means for f of any number less than 0, probability that x less or equal to that number is 0. Probability that x less or equal to -1, that's impossible. X starts from 0. Probability of any number less than 0 is 0. So the probability f of any number less than 0 is 0 until we reach 0. Once we reach 0, it jumps up to 16 over 81. Once we reach 0, it jumps up to 16 over 81. Then keep going. The next value is 1. Next x value is 1. Keep going until 1. When we reach 1 here, f of 0 is probability that x less or equal to 0. That's f of 0, which is 16 over 1. For f of 1, that's probability that x less or equal to 1. If x is less or equal to 1, x could be either 0 or 1. I get f of 0 plus f of 1. That's 16 over 81 plus 32 over 81, which is 48 over 81. So once I reach 1 here, once x reach 1, it jumps up to 48 over 81. 50 is here, it jumps up to 48 over 81, somewhere here. Then stay at 1 until we reach the next x value. Stay at 1 until we reach the next x value. Next x value is 2. We reach 2. When we reach 2 here, we try to find f of 2. F of 2 is probability that x less or equal to 2. In the support here, x less or equal to 2. If x is less or equal to 2, x could be either 0, 1, or 2. F of 0 is 16 over 81. F of 1 is 32 over 81. F of 2 is 24 over 81. Together I get 72 over 81. Together I get 72 over 81. So once I reach 2 here, it jumps up to 72 over 81, somewhere here. Then it stays at 70. Stay here at 72 over 81 until it reaches next x value. Next x value is 3. It stays at 72 over 81 until we reach the next s value. When we reach 3 here, let's compute f of 3. F of 3 is probability that x less or equal to 3. In the support, if x is less or equal to 3, x must be 0, 1, 2, and 3. So add up f of 0, f of 1, plus f of 2, plus f of 3. Together we have 16 over 81 plus 32 over 81 plus 24 over 81 plus 8 over 81. Together is 80 over 81. So once x reaches 3, it jumps up to 80 over 81, somewhere here. Then keep going, stay here. It stays at 80 over 81 until we reach the next s value. The next s value is 4. Next x value is 4. It stays at 4. It stays at 80 over 81 until x reaches 4. When x reaches 4, let's compute f of 4. F of 4 is probability that x less or equal to 4. F of 4 is probability that x less or equal to 4. If x is less or equal to 4, x could be 0, 1, 2, 3, 4. If x is less or equal to 4, x could be 0, 1, 2, 3, 4. So we have f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. I don't have enough space here, but if we add them up, the total probability must be 1. If we add them up, the total probability must be 1. So f of 4 equal to 1. When x reaches 4, the CDF jump up to 1. And then it stays at 1 forever. It stays at 1 forever. For example, for f of 5, we are looking for probability that x less or equal to 5. If x is less than or equal to 5, x could be either 0, 1, 2, 3, or 4. So add them up. F of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. The same as the previous row. I get 1 here. So f of 4 is 1. F of 6 is 1. For any x value, for any value larger than 4, f of that value is always 1. So the CDF stays at 1. The CDF stays at 1 forever. On the left side, it stays at 0 forever. On the left side, for any value less than 0, if I plug in, the CDF is 0. So that's the graph of the CDF. If we try to write the CDF, we can write it like this. F of x is 0 if x is less than 0. F of x equal to 16 over 81. F of x equal to 16 over 81 if x is between 0 and 1. Including 0, not including 1. Then here, f of x equal to 48 over 81 if s is between 1 and 2. Including 1, not including 2. Including 1, not including 2. And here, f of x is 72 over 81. F of x here is 72 over 81. If s is between 2 and 3, including 2, not including 3. Next, f of x could be 80 over 81 here. 80 over 81. When x is between 3 and 4. Including 3, not including 4. And finally, f of x will be 1. Finally, f of x equal to 1 if s is greater than or equal to 4. If s is greater than or equal to 4. That's the CDF. That's the CDF for this binomial distribution with n equal to 4, p equal to 1/3. So in general, to find the PDF, we sketch its graph first, then find a function based on the graph. Next example, assume the CDF of the random variable x is given below. F of x equal to 0 if x is less than -2. F of x equal to 0.1 if s is between -2 and 0, including -2. F of x is 0.3 if s is between 0 and 1, including 0. F of x is 0.7 if s is between 1 and 3, including 1. F of x equal to 1 if s is greater than or equal to 3. Here, capital F represents the CDF. This F is capital. This x must be lowercase. F of x, this capital F of x represents the CDF, the cumulative distribution function. Now, based on this function here, part A, find each of the following probabilities. First one, how do we find the probability that x is less than or equal to 0. How do we find the probability that x is less than or equal to 0? We know that f of x, by the definition of CDF, f of x equal to probability that x is less than x, random variable x is less than x. So it can be rewritten as probability that x less or equal to x equal to f of x. Probability that x less or equal to x equal to f of x. So here, probability that x less or equal to 0 equal to f of 0. For f of 0, I can read it from the equation. I can read it from this function here. For f of 0, I can read it from this function. 0 is somewhere here. S equal to 0 is here. So when s is greater than or equal to 0, f of x is 0.3. When s equal to 0, f of x is 0.3. That means probability that x less or equal to 0 is 0.3. Next, how do we find probability that x is less or equal to 1? How do we find the probability that x is less or equal to 1? If we try to match this formula here, probability that x is less or equal to 1, that's f of 1. And in the CDF, when s equal to 1, f of x is 0.7. Next, how do we find the probability that x is strictly less than 0? How do we find the probability that x is strictly less than 0? Now, keep this idea in mind. If we try to find the probability that x is strictly less than a number a, there's no such formula for this. There's no such formula for this. For a formula, we must have x greater than or equal to some constant. In the formula, we must have x less than or equal to some constant. But here we have x strictly less than a. What can we do here? We try to rewrite this probability in this form. So what we can do is here, I take limit. Since x is less than a, I can take limit as s approach to a from left side. Then this probability that x less than a can be rewritten as probability that x less or equal to x. If x approach to a from left side means x is a little less than a. Suppose a is here. X is a little less than a. X is a little less than a. So the probability that x less than a is the same as probability that x less or equal to a as probability that x less or equal to x as x approach to a from left side. When x approach to a from left side, these two probabilities they are exactly the same. As x approach to a from left side, as x approach to a from left side, this limit is the same as this probability here. And probability that x less or equal to a, probability that x less or equal to x, that's f of x. Probability that x less or equal to x, that's by definition of CDF, that's capital F of x. Then we take limit. When we take limit, we have f of a from left side. When we take limit, we have f of a limit from left side. F of a. This is a shortcut for this limit. F of a from left side is the shortcut as the limit s approach to a from left side. F of x. This is the shortcut for this limit. They are exactly the same. This is the shortcut for this limit. So, probability that x less than a. For probability that x strictly less than a, I can write it as f of a from left side. F of a taking limit from left side. Probability that x strictly less than a, that's f of a taking limit from left side. So similarly, I can write x. Similarly, I can write probability that x is less than x equal to f of x taking limit from left side. Probability that x less than x is f of x taking limit from left side. So probability that x strictly less than x is f of x taking limit from left side. Keep these two formulas in mind. Keep these two formulas in mind. Those are the two key formulas. Keep these two formulas in mind. Keep these two formulas in mind. Probability that x strictly less than x is f of x taking limit from left side. So probability that x strictly less than 0, that's f of 0 taking limit from left side. F of 0 taking limit from left side. If I take limit from left side, means x is strictly less than 0. X is a little less than 0 here. X won't be 0, but x is a little less than 0. So when x is a little less than 0, f of x is 0.1. What's the probability that x is strictly less than 1? So use the formula here. Probability that x strictly less than 1 is f of 1, taking limit from left side. F of 1, taking limit from left side. 1 is here. If I take limit from left side, x is less than 1. X is a little less than 1. So when x is a little less than 1, f of x is 0.3. Next. How do we find probability that x equal to negative 2? How do we find probability that x equal to negative 2? When we have x equal to negative 2, we try to put it in this form. Then we can use capital F to find a solution. We try to rewrite this probability in this form first, in these two forms first. Then we can use the function to find the probability. First step, try to rewrite this probability in these two forms first. Then we can use the CDF to find the probability. What can we do here? Now think of this. For probability that x equal to negative 2, think of this. Probability that x less or equal to negative 2. Take away probability less than negative 2, what do we get? Probability that x is less than or equal to negative 2. That means x is either less than negative 2 or x is equal to negative 2. That means either x is less than negative 2 or x is equal to negative 2. If I take off the probability that x is less than negative 2, if I subtract, take off the probability that x is less than negative 2, what's left is probability that x equal to negative 2. So probability that x equal to negative 2 can be rewritten as probability that x is less than or equal to negative 2 minus probability that x is less than negative 2. Probability that x equal to negative 2 can be rewritten as probability that x is less than or equal to negative 2 minus probability that x is less than negative 2. So that's the formula for probability that x equal to some constant. So keep this formula in mind. Probability that x equal to some constant, it can be rewritten as probability that x less or equal to the constant minus probability that x is less than the constant. Probability that x equal to some constant is probability that x less or equal to the constant minus probability that x is strictly less than the constant. So for probability that x equal to negative 2, I can write probability that x is less than or equal to negative 2 minus probability that x is strictly less than negative 2. Then rewrite this in terms of capital F. You rewrite these two probability in terms of CDF. This is f of negative 2 by the first formula. This is f of negative 2 taking limit from left side. That's the second formula. This is f of negative 2 taking limit from left side. F of negative 2. F of negative 2 is here. When x equal to negative 2, f of x is 0.1. F of negative 2 taking limit from left side. That means x is a little less than negative 2. When x is a little less than negative 2, f of x is 0. So 0.1 minus 0 is 0.1. Next, what's the probability that x equal to 0? What's the probability that x equal to 0? probability s equal to 0 can be rewritten as probability that x less or equal to 0 minus probability that x is less than 0. Probability that s equal to 0 can be written as probability that x is less than or equal to 0 minus probability that x is less than 0, using this formula here. Then rewrite these two probabilities in terms of the CDF. First one, probability that x is less or equal to 0 can be rewritten as f of 0. X is less than 0, where x is strictly less than 0. That's capital F of 0, taking limit from left side. F of 0, when s is 0, f of x is 0.3. For f of 0 from left side, x is strictly less than 0. When x is a little less than 0, f of x is 0.1. 0.3 minus 0.1 is 0.2. Next, what's the probability that x equal to 1? What's the probability that s equal to 1? Probability that s equal to 1 can be rewritten as probability that x less or equal to 1 minus probability that x is strictly less than 1. Probability that x is less or equal to 1, that's CDF f of 1. Probability that x less than 1, x strictly less than 1, that's a CDF f of 1, taking limit from left side. F of 1, when s equal to 1, f of x is 0.7. When x equal to 1, f of x is 0.7. For f of 1, taking limit from left side, that means x is a little less than 1. If I take limit from left side, x is a little less than 1. When x is a little less than 1, f of x is 0.3. 0.7 minus 0.3 is 0.4. Next. Let me remove this part. Next, how do we find the probability that x is s equal to 3? Probability that s equal to 3 is probability that x less or equal to 3 minus probability that x is strictly less than 3. This is CDF f of 3 minus CDF f of 3, taking limit from left side. F of 3, when s equal to 3, f of x equal to 1. When s equal to 3, f of x equal to 1. F of 3, taking limit from left side, that means x is a little less than 3. If x is a little less than 3, f of x is 0.7. 1 minus 0.7 is 0.3. Next, how do we find the probability that x is between -2 and 1? How do we find the probability that x is between -2 and 1? So, for inequality like this, we try to rewrite it in this form. For inequality looks like this, we try to rewrite this inequality in this form first, then use the CDF to find the probability. What can we do here? X is between -2 and 1, including 1. What can we do here? We know that this line here, from -infinity to 1, this line represents x less than or equal to 1. This line segment here represents x less or equal to 1. We try to find the line segment that x is between -2 and 1, including 1, not including -2. So we try to find the line segment here from -2 to 1. This line segment is x equal to -2, x between -2 and 1, including 1. So if I take this line segment, remove the tail here. If I take this line segment, remove the tail here, I get a line segment from 1 to -2. How do I remove the tail? This tail can be represented by x less or equal to -2. Since I try to remove -2, I need to remove x for all x that's less than or equal to -2. So from the entire line segment, if I remove this line segment here, if I remove this tail here, x less or equal to -2, what's left is probability that x between -2 and 1. So probability that x between -2 and 1, it can be written as probability that x is less or equal to 1. That's the entire line segment. Remove this tail here. Remove this tail here. Remove probability that x is less than or equal to -2. If I take probability that x less or equal to 1, remove the tail here, what's left is a line segment, probability that x between -2 and 1, including 1. Then rewrite each of them using the CDF. Rewrite each of them using the CDF. This is f of 1, this is f of -2. Then for f of 1 and f of -2, we can read it from the function. F of 1, when s equal to 1, f of x is 0.7. Next, f of -2. When x is -2, f of x is 0.1. When x is -2, f of x is 0.1. So 0.7 minus 0.1 is 0.6. That's the answer to this. Next, what's the probability that x is between -2 and 1? What's the probability that x is between -2 and 1, including both endpoints? We can use the same technique. First of all, draw the line segment from negative infinity to 1. This line segment represents x is less or equal to 1. We try to get the line segment here, x from -2 to 1. We try to obtain this line segment. So from the total, we can try to remove the tail and get the middle piece. We can try to remove the tail and get the middle piece. The middle piece here is x between -2 and 1. We try to remove the tail. What's the tail here? The tail includes everything less than -2. Now this time we don't remove the endpoint. Because in the line segment here it includes a -2. So here we don't remove the endpoint. So remove x that's less than -2. We remove all x that's strictly less than -2. From the total line segment, if I remove this tail here, what's left is x between -2 and 1. So probability that x between -2 and 1 can be written as probability that x is less than or equal to 1 minus probability that x is strictly less than -2. Then this is capital F of 1. This is capital F of -2. Since there's no equal sign here, it's capital F of -2, taking limit from left side. F of 1, for f of 1, when s equal to 1, f of x is 0.7. F of -2, limit from left side. For f of -2, limit from left side, that means x is a little less than -2. When s is a little less than -2, f of x is 0. So the answer is 0.7. Next. What's the probability that x is strictly between -2 and 1? What's the probability that x is strictly between -2 and 1? Do the same thing. Draw a line segment first. I can first of all draw a line segment from negative infinity to 1, not including 1. This time I don't include 1 because the 1 is not included. Here, this line segment is x less than 1, x strictly less than 1. We try to obtain the line segment from -2 to 1. Assume -2 is here. We try to obtain this line segment here. That means from total line segment, we need to remove the tail. This line segment is x from -2 to 1, not including -2. if we don't include negative 2 here, that means we need to remove negative 2. So remove all of x such that x is less than or equal to negative 2. If we don't include an endpoint, that means we need to remove an endpoint. So remove all x such that x is less than or equal to negative 2. So this probability can be rewritten as probability that x is less than 1 minus the probability that x is less than or equal to negative 2. What's left is this line segment. Probability that x is strictly less than 1. That's f of 1. Taking limit from left side. Probability that x is less than or equal to negative 2. That's capital F of negative 2. If there's equal sign, that's CDF f of negative 2. Then you use the function. Go to the function, find the value. F of 1, limit from left side. That means x is a little less than 1. We use f of x equal to 0.3. F of negative 2. When s equal to negative 2, f of x is 0.1. So negative 3, 0.3 minus 0.1. 0.3 minus 0.1 is 0.2. That's the probability that x is between negative 2 and 1. Next, what's the probability that s is between negative 2 and 1, including negative 2? What's the probability that s is between negative 2 and 1, including negative 2? So similarly, I can draw a line segment first. Assume this line segment here is x strictly less than 1. We try to obtain the line segment x is between negative 2 and 1. Assume negative 2 is here, and negative 2 is included. We try to obtain this line segment here. That means from the total line segment, I need to remove the tail. Here, this tail can be represented that x is strictly less than negative 2. Since negative 2 is included in the line segment here, when we remove the tail, we don't remove negative 2. So remove a set of all x such that x is strictly less than negative 2. This line segment here is x between negative 2 and 1, including negative 2 but not 1. Including negative 2 but not 1. Then use the formula. This probability can be rewritten as probability that x strictly less than 1, the total line segment, minus the tail, probability that x is strictly less than negative 2. The total line segment, remove the tail. What's left is probability that x between negative 2 and 1, including negative 2 but not 1. Then use the formula. This is f of 1 from left side. When x is strictly less than 1, we have f of 1 limit from left side. When x is strictly less than negative 2, we have f of negative 2 limit from left side. Then look at the function. F of 1 limit from left side. Limit from left side means x is a little less than 1. When x is a little less than 1, we use f of x equal to 0.3. Next, minus f of negative 2 limit from left side. That means x is a little less than negative 2. When x is a little less than negative 2, f of x is 0. 0.3 minus 0 is 0.3. That's the probability that x is between negative 2 and 1. Part B, find the probability function of x. Based on the CDF of x, how do we find the probability function of x? So observe here, this CDF is a piecewise defined constant function. This CDF is a piecewise defined constant function. So for a piecewise defined constant function, if we try to find its probability function, for a piecewise defined CDF, if we try to find a probability function, look at the gaps. We have one gap at negative 2, another gap at 0, another gap at 1, another gap at 3. For piecewise defined constant CDF, if we try to find a PDF, we try to find the probability at the gaps first. We try to find the probability at the gaps first. For a piecewise defined constant CTF, if we try to find a PDF, if we try to find a probability function, we try to find a probability at the gaps here. Try to find a probability at the gaps first. We have 1 gap, 2 gap, 3 gap, 4 gap. So we try to find f of -2, f of 0, f of 1, f of 3. I mean lowercase f. Try to find f of -2, f of 0, f of 1, and f of 3. Find the probability at the gaps first. If we try to find a probability function, let's find the probability at the gaps first. Here the gap is -2, 0, 1, and 3. Let's find the probability at the first gap. What's the f of -2? For a discrete random variable, probability that s equal to a constant is f of the constant. F of x, probability that s equal to x is always f of x. That's for discrete random variable. Keep in mind. If x is discrete random variable, f of -2 is probability that x equal to -2. F of -2 is probability that s equal to -2. Probability that s equal to -2. From part A, we know that probability that s equal to -2 is 0.1. Probability that s equal to -2 is 0.1. F of 0 is a probability that s equal to 0. F of 0 is probability that s equal to 0. From part A, we know that probability that s equal to 0 is 0.2. What's f of 1? F of 1 is probability that s equal to 1. F of 1 is probability that s equal to 1. If s equal to 1, the probability that s equal to 1, from part A we know that probability that s equal to 1 is 0.4. Next, find f of 3. F of 3 is probability that s equal to 3. F of 3 is probability that s equal to 3. When s equal to 3, probability that s equal to 3, from part A we know that probability that s equal to 3 is 0.3 here. So we can check here. F of -2, 0, 1, 3, they are all positive. And if I add them up, their sum here is 1. If I add them up, their sum is 1. If they are all between 0 and 1 and their sum is 1, this function f is a probability function. So f of x equal to 0.1 if s equal to 2. F of x equal to 0.2 if s equal to 0. F of x equal to 0.4 if s equal to 1. F of x equal to 0.3 if s equal to 3. This is a probability function. Next example, let the CTF of a random variable x be defined as the following graph. So suppose this graph represents the CTF of x. Find each of the following probabilities. First one. What's the probability that x is less than or equal to 0? What's the probability that x is less than or equal to 0? If we try to find probability based on the CTF, keep two formulas in mind. Probability that x less or equal to x is f of x. Probability that x strictly less than x is f of x but taking limit from left side. If we try to find probability based on the CDF, keep these two formulas in mind. We try to write probability in these two forms, then find a probability. Probability that x is less than 0, less or equal to 0, is in the first form. So that's f of 0, that equal to f of 0. For f of 0, I can read it from the graph. When s is 0, f of x is 0.3. When s is 0, f of x is 0.3. Next, find a probability that x is s equal to 0. Find a probability that s equal to 0. For probability that s equal to 0, we write it as probability that x less or equal to 0 minus probability that x is less than 0. Because we cannot find probability that s equal to 0 directly from CDF. We cannot find probability that s equal to 0 directly from CDF. We must rewrite probability that s equal to 0 in these two forms, in terms of these two probabilities first. Then we can use the formula to find the probabilities. So I first of all rewrite probability that s equal to 0 in terms of these two probabilities. Then these two probability that x less or equal to 0, that's f of 0. That's the first case, f of 0. Probability that x approaches x is strictly less than 0. Probability that x is strictly less than 0. That's f of 0, taking limit from left side. According to the second formula, that's f of 0, taking limit from left side. F of 0, where s is 0, we have 0.3. The starting point is here. We have 0.3. F of 0, taking limit from left side. If I take limit from left side, means it doesn't reach 0. 0 is here. Limit from left side is 0. 0.3 minus 0 is 0.3. Part C. What's the probability that x is greater than 0? What's the probability that x is strictly greater than 0? If s is greater than 0, for the probability s is greater than 0, we try to rewrite this probability in terms of these two forms. Here we can think of the complement. Probability that s greater than 0 can be rewritten as 1 minus probability that x is less than or equal to 0. The opposite that s is greater than 0 is x less than or equal to 0. Then plug in probability that x less or equal to 0. Probability that s less or equal to 0. This is f of 0. F of 0, when s is 0, we have 0.3 here. 1 minus 0.3 is 0.7. Next, part D. What's the probability that x is strictly less than 1? What's the probability that x is strictly less than 1? When x is strictly less than some number, probability that x is strictly less than some number is f of 1, taking limit from left side. F of 1, taking limit from left side. F of 1, taking limit from left side. 1 is here. Since it's connected, it's continuous. It doesn't matter limit from left side or right side, it's the same. So f of 1, limit from left side is 0.3. Since the function is continuous, it doesn't matter if the limit is from left side or right side, they all stay the same. So f of 1, limit from left side is 0.3. Part E. What's the probability that s equal to 1? Part E. What's the probability that s equal to 1? Part E. What's the probability that s equal to 1? For probability s equal to 1, we try to write it in terms of these two probabilities. For probability that s equal to 1, we try to write it in terms of these two probabilities. So probability that s equal to 1 can be rewritten as probability that x less or equal to 1, take away probability that x is strictly less than 1. Probability that x less or equal to 1, that's f of 1. Probability that x less than 1, x strictly less than 1, that's f of 1. Taking limit from left side. f of 1 is 0.3. f of 1, taking limit from left side. For f of 1, since this is continuous function, f1 is continuous. Limit from left side, right side, they're all the same. So f of 1, limit from left side is also 0.3. 0.3 minus 0.3 is 0. So probability that s equal to 1 is 0. Next, what's the probability that x is greater or equal to 1? When we have probability that s is greater or equal to 1, we try to put it in these two forms. So I can use the complement, write it as probability that 1 minus probability that x is less than 1. We can use complement, rewrite this probability as 1 minus probability that x is less than 1. Probability that x is less than 1, that's f of 1, limit from left side. Probability that x is less than 1, that's f of 1, limit from left side. And f of 1, limit from left side. For f of 1, limit from left side, it's 0.3. 1 minus 0.3 is 0.7. That's the probability that x is greater than or equal to 1. Part G. What's the probability that x is less than or equal to 4? What's the probability that x is less or equal to 4? Probability that x is less than or equal to 4, it's in this form. So that equal to f of the constant, f of 4. f of 4 in the picture, the starting point is 0.8 here. So f of 4 is 0.8. What's the probability that s equal to 4? For probability that s equal to 4, try to put it in terms of these two probabilities. Try to rewrite this probability in terms of these two probabilities. We cannot get probability s equal to 4 directly from the CDF. We cannot get probability of s equal to 4 directly from the CDF. We must rewrite this probability in terms of these two probabilities first. So probability that s equal to 4 can be rewritten as probability that x is less than or equal to 4 minus probability that x is less than 4. Probability that x is less or equal to 4, that's f of 4. Probability that s is less than 4, that's f of 4, limit from left side. Then f of 4. For f of 4, 4 is here. Look at the starting point. Starting point here, starting point at 4 is 0.8. Starting point at 4 is 0.8. Minus f of 4, limit from left side. For f of 4, limit from left side, what do we get? 4 is here. Limit from left side is here, which is 0.6. f of 4, limit from left side is 0.6. 0.8 minus 0.6, we have 0.2. 0.8 minus 0.6, that's 0.2. Next, how do we find probability that x is greater than or equal to 4? How do we find probability that s is greater than or equal to 4? We can use the complement. Try to rewrite this probability in terms of these two probabilities first. In terms of in the form that x is less than or equal to some constant, or x is less than some constant. We cannot find a probability directly from the CDF in this form. In this form, we cannot find a probability directly from the CDF. So let's rewrite this probability. We can try to rewrite this probability using the complement. Probability that s is greater or equal to 4 can be rewritten as 1 minus probability that x is strictly less than 4. And we know that probability that x less than 4 is f of 4, limit from left side. 1 minus f of 4, taking limit from left side. f of 4, limit from left side is 0.6. 1 minus 0.6 is 0.4. Next, Next, find probability that x is between 2 and 4. Find probability that x is between 2 and 4. So for this probability, we can find this probability directly. We must write this probability in terms of these two probabilities. So we can first of all draw a line segment from net infinity to 4. This line segment represents x less than 4. We try to find a line segment that x is between 2 and 4. We try to find this line segment here. X is between 2 and 4. That means we need to remove this tail here. Since 2 is not included in this line segment, that means we need to remove 2. If we remove 2, we need to remove all x that's less than or equal to 2. We need to remove all x that's less than or equal to 2. Then what's left is the line segment from 2 to 4. If I remove everything less than or equal to 2, what's left is a line segment from 2 to 4. So this probability can be rewritten as probability that x less than 4, the entire line segment, minus probability that x is less than or equal to 2. Remove the tail. What's left is this line segment. This is f of 4, limit from left side, since there's no equal sign below inequality. This is f of 4, limit from left side, minus f of 2, since there's equal sign below inequality, that's exactly f of 2. Then for f of 4, limit from left side. For f of 4, limit from left side. 4 is here, limit from left side is 0.6. f of 2. f of 2. For f of 2, the value here is 0.4. Since it's connected, it's continuous. Since the function is continuous, it doesn't matter if the limit from left side or right side, the limit is the same. It's 0.3 here. f of 2, the limit is, for f of 2 is 0.3. 0.6 minus 0.3 is 0.3. Next, find the probability that s is between 0 and 6. Find the probability that s is between 0 and 6. First of all, draw a line segment from net infinity to 6. That's the line segment x less than 6. We try to find a line segment x from 0 to 6, including 0, not 6. We try to find this line segment here. So we can take the total line segment, remove the tail here. If I remove tail, I have line segment x from 0 to 6. Since 0 is included in the line segment, so we don't remove 0. I remove everything strictly less than 0. I remove everything strictly less than 0. So from total line segment, if I remove the tail, x less than 0, what's left is this line segment x between 0 and 6 here. So that's probability that x less than 6 minus probability that x is less than 0. This is f of 6, limit from left side. This is f of 0, limit from left side. f of 6, limit from left side. 6 is here. If I take limit from left side, I get 0.8. For f of 0, limit from left side. f of 0, limit from left side, that's 0. f of 0, limit from left side is 0. 0.8 minus 0 is 0.8. So that's the probability that s is between 0 and 6, including 0. Next example, let the CDF of a random variable x be defined as f of x equal to x over s plus 2 if s is greater than or equal to 0, and 0 otherwise. Find each of the following probabilities. Part A. Find the probability that x is less than or equal to 1. We'll try to find probability based on the CDF. We try to rewrite every probability in terms of these two forms. Probability that x less or equal to some number, or probability x strictly less than some number. The first form, probability that x less or equal to some constant x, that's f of x, capital F of x. The probability that x less than x is f of x, taking limit from left side. Probability that x less or equal to 0, that's in the first form. So it can be divided as f of 1. It can be divided as f of 1. For f of 1, we plug in 1 here into the function f, into the CDF function f. If I plug in 1, 1 is greater than 0. So I plug in 1 into the first function here. If I plug in 1, I get 1 over 1 plus 2. That's 1/3. That's the probability that x less or equal to 1. Part B. What's the probability that x is strictly less than 1? What's the probability that x is strictly less than 1? Probability that x is less than 1 match the second form. So I can use the formula that equal to f of 1, taking limit from left side. But when x is greater than 0, f of s is continuous. If it's continuous, it doesn't matter the limit is from left side or right side. We plug in 1 directly. I get 1 over 1 plus 2, which is also 1/3. Part C. What's the probability that s equal to 1? When we have probability s equal to 1, we cannot find a probability directly from the CDF. We must rewrite this probability in terms of these two forms first. Probability that x equal to 1 can be rewritten as probability that x less or equal to 1 minus probability that x strictly less than 1. Probability that x is less or equal to 1, that's f of 1. Probability that x is strictly less than 1, that's f of 1. Taking limit from left side. And from part A and part B, we know that f of 1 is 1/3. F of 1 taking limit from left side is also 1/3. 1/3 minus 1/3 is 0. 1/3 minus 1/3 is 0. That's probability that s equal to 1. Part D. What's the probability that x is greater than -1? What's the probability that s is greater than -1? We try to rewrite this probability in these two forms first, in terms of these two forms first. We cannot find the probability directly from the CDF. We must rewrite the probability in terms of these two forms first. Then use this formula to find the probability here. For probability that s is greater than -1, we can use complement. That's 1 minus probability that x is less or equal to -1. That can be written as 1 minus probability that x less or equal to -1. Let's match the first form here. That's capital F of -1. F of -1. Here, -1 is not greater than 0. So f of -1 must be 0. Since -1 is not greater than 0, f of -1 must be 0. 1 minus 0 is 1. Probability that s is greater than -1 is 1. That means x is always greater than -1. Part E. What's the probability that x greater than or equal to 2? What's the probability that s is greater than or equal to 2? When we have x greater than or equal to 2, we try to rewrite this probability in terms of these two forms first. And that can be rewritten as probability that 1 minus probability that x strictly less than 2. Probability that x less than 2, that's f of 2, taking limit from the left side. And since f is continuous, when s is greater than 0, f is continuous. So it doesn't matter limits from left side or right side. I can plug in 2 directly. Since when s is 2, s is greater than 0, f of s is continuous. And since f of s is continuous, it doesn't matter limits from left side or right side. They are all the same. I can plug in 2 directly. If I plug in 2 directly for x, I get 2 over 2 plus 2. 2 over 2 plus 2 is half. 1 minus half is half. That's probability that x is greater than or equal to 2. Part F. What's the probability that s is between 3 and 4? What's the probability that s is between 3 and 4? we need to rewrite this probability in terms of these two forms first, otherwise we can't find it directly. So this probability can be written as, we can draw a number line first. We can first of all draw a line segment from net infinity to 4. This is line segment x less than 4. We try to obtain a line segment from 3 to 4, not including 3. We want this piece, so I need to remove the tail. We need to remove the tail. The tail here is x. This line segment is s between 3 and 4. If I try to remove the tail, I need to remove number 3 here, because 3 is not included in this line segment. I need to remove 3. If I remove 3, I need to remove all x that's less than or equal to 3. So I need to remove this tail. From the total line segment, if I remove this tail, I get this line segment here. That's probability that x is less than 4, probability that x is less than 4, minus probability that, minus the tail, probability that x is less or equal to 3. Probability that x is less than 4. Probability that s is less than 4, that's f of 4, taking limit from left side. Probability that x is less or equal to 3, that's f of 3. For f of 4, limit from left side. For f of 4, limit from left side. I plug in 4 directly here. When s is greater than 0, f of s is continuous. When it's continuous, it doesn't matter the limit is from left side or right side. They're always the same. So I can plug in 4 directly. If I plug in 4, I get 4 over 4 plus 2. Next, for f of 3, I plug in 3. 3 is greater than 0. I plug in 3 here. I get 3 over 3 plus 2. That's 2 over 3 minus 3 over 5, which is 1 over 15. Next, let me show you some properties about CTF. Let x be a random variable. With CTF, with the cumulative distribution function, f of x. Usually we use capital F to represent the CTF. First property, if I take a limit as approach to net infinity, for the CTF, if I take a limit as approach to net infinity, this limit is always 0. If I take a limit as approach to infinity for the CTF, this limit is always 1. If I take a limit as approach to net infinity, this limit is always 0. If I take a limit as approach to partial infinity, this limit is always 1. We can look at the picture here. It may make more sense for you. In the first example here, we see that as approach to net infinity, f of x approach to 0. As x approach to infinity, f of x stays at 1 forever. So on the left side, it approaches to 0. On the right side, it approaches to 1. That's a property of the CTF. The limit as approach to net infinity, f of x is 0. And the limit as approach to infinity, f of x is 1. That's the first property. Second property, if x is a continuous random variable, if s is a continuous random variable, then the CTF f of x is always continuous. is always a continuous function. On the interval from negative infinity to infinity. If x is a continuous random variable, then the CDF f of x is always a continuous function on the interval from negative infinity to infinity. That's the second property. The third property, and that's the most important one. The third property is the most important property. If x is a continuous random variable, if s is a continuous random variable, with probability density function (PDF), with the probability density function, usually we use lowercase f represent the PDF. Usually we use lowercase f represent the PDF probability density function. Then the derivative of the CDF f of x equal to the PDF f of x. The derivative of f of x equal to the PDF f of x, because the derivative f of x equal to the derivative of the probability of x is less or equal to x, because f of x, CDF f of x equal to probability that x is less or equal to x. So if I take derivative for f of x, that means I take derivative for probability that x is less or equal to x. And we know that probability that x is less or equal to x, that's the integral from negative infinity to x, f of x dx. That's the derivative of the integral from negative infinity to x, f of x dx. And in general, to avoid confusion here, we write f of t dt here, because this x and this s cannot be the same letter. To avoid confusion, we write f of t dt here. F of t dt here. Then for this integral here, this is an improper integral. So we can write it like limit as a approach to negative infinity. I can write improper integral as limit a approach to negative infinity. Derivative of the integral from a to x, f of t dt. Then by fundamental theorem of calculus, this derivative here is the limit a approach to negative infinity. This derivative here is f of x. I plug in upper limit for the variable. That's fundamental theorem of calculus. We plug in upper limit for the variable. And then, since a is a constant, there's no a here. This is equal to f of x. So that's why derivative of capital F of x equal to f of x. That's the third property. That's why derivative of f of x, derivative of the CDF is the PDF. Derivative of the CDF is the PDF. So keep this rule in mind. If we know the CDF and we try to find the PDF, assume S is a continuous random variable. If we know the CDF, we try to find the PDF. We take derivative. If we know the CDF, we try to find the PDF. We take derivative. Now, in order to go backward, if we know the PDF, we try to find the CDF. We can take the antiderivative. Keep this rule in mind. If we know the CDF and we try to find the PDF, take derivative. If we try to go backward, if we know the PDF, we try to find CDF, we try to go backward. find the antiderivative. So keep this rule in mind. From CDF to PDF, take derivative. And from PDF to CDF, take an antiderivative. Next example. In example 5, in the previous example, find the PDF of x. In the previous example, find the PDF of x. In the previous example, we know the CDF. F of x is x over s plus 2 if s is greater than 0 and 0 otherwise. In the previous example, f of x is x over s plus 2 if s is greater or equal to 0 and 0 otherwise. So that's the CDF. If we try to find the PDF, what should we do? If we know the CDF and we try to find the PDF, take derivative. So take derivative. How can we take derivative here? First of all, draw number line. First interval is s greater than or equal to 0. When s is greater or equal to 0, f of x is x over s plus 2. When s is greater than 0, f of x is x over s plus 2. And the other interval here is x less than 0. The other interval here is x less than 0. And for x less than 0, f of x is 0. Then, since here we know the CDF, we try to find the PDF, so we take derivative. Derivative of 0. Derivative of 0 is 0. How do we take derivative here? How do we take derivative here? For this derivative, we can use quotient rule. For this derivative, we can use quotient rule. If we use quotient rule, what do we get? Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom square. That can be rewrite as x minus x can cancel. We have a 2 left on the numerator over x plus 2 square. That's the derivative of x over s plus 2. So for the final answer, we write f of x equal to, write 0 later, equal to 2 over x plus 2 square if x is greater than 0, 0 otherwise. The reason I don't include inequality here, the reason I don't include equal sign here is because this is a piecewise function. This is a piecewise function. This is capital F. The CDF is a piecewise function. In general, for a piecewise function, and the boundary, in general, for a piecewise defined function, in the boundary there's a corner or sharp angle. In general, for a piecewise defined function in the corner in the boundary, there's a corner or sharp angle. Usually it's not differentiable. So f of x, since we find f of x by doing derivative, and it's not differentiable at the endpoint here, so we don't include an endpoint. We set equal to 0. We set f of 0 equal to 0. We set the boundary equal to 0. So when we write the PDF, we don't include an endpoint. We set equal to 0. We set equal to 0 automatically, because usually it's not differentiable at the boundary of the intervals. For any piecewise defined function, usually there's a sharp angle or corner at the boundaries of the intervals. Usually it's not differentiable at the endpoint of the boundaries. So we don't include the endpoint of the boundaries. We write x strictly greater than 0. We set f of 0 equal to 0. We set the boundary equal to 0. So 0 otherwise. So be very, very careful. When we find PDF based on taking derivative from the CDF, we don't include the endpoint. We write x strictly greater than 0. If 0 is the endpoint, we don't include the endpoint. We write x strictly greater than 0. Next example, let the CDF of the random variable x be defined as f of x equal to 0 if x is less than 0, f of x equal to 1 over a s squared if s is between 0 and 2, including 0, f of x equal to 1 over 4x if s is between 2 and 4, including both 2 and 4, f of x equal to 1 if s is greater than 4. find the PDF of x. So if we know the CDF, we try to find the PDF, we take derivative. If we know the CDF, we try to find the PDF, take a derivative. If we know the PDF and try to find the CDF, take antiderivative. In this problem, we know the CDF and try to find the PDF, so we take derivative. First of all, let's draw the function. Let's run the function in the number line. Let's run the CDF f of x in the number line. So if x is less than 0, f of x equal to 0. If s is between 0 and 2, if s is between 0 and 2, f of x is 1 over a x squared. If s is between 2 and 4, f of x is 1 over 4x. If s is greater than 4, f of x equal to 1. Then, since we know the CDF and try to find the PDF, so we take derivative. If we take derivative of 0 is 0. Derivative of 1 over a x squared is 1 over 4x. Derivative of 1 over 4x is 1 over 4. And derivative of 1 is 0. Derivative of any constant is 0. So for the final answer, run the PDF here. Write 0 in the last step. Write 0 in the last step. So first of all, f of x equal to 1 over 4x. If s is between 0 and 2, because at the endpoint, usually in the function, the CDF is not differentiable. Usually at the endpoint and the boundary point, the CDF is not differentiable, so we don't include the endpoint. S is between 0 and 2, don't include the endpoint. And f of x equal to 1 over 4. If s is between 2 and 4, don't include the endpoint. In general, at the endpoint and the boundary point here, the CDF is not differentiable. Usually there's a sharp angle or corner and the boundary point, they are not differentiable. So we don't include the endpoint. And 0 otherwise. In the CDF, we say f of 0, f of 2, f of 4. We say all the boundary points equal to 0. So 0 otherwise. Next example, let the PDF of a random variable x be f of x, where f of x is e raised to negative x if x is greater than or equal to 0, and f of x equal to 0 otherwise. Find the CDF of x. So here, if we know the PDF and we try to find the CDF, we take antiderivative. Here, let me show you how to take an antiderivative. First of all, draw the number line. Run the PDF on the number line. Draw number line first. Number line is from negative infinity to infinity. If s is greater than or equal to 0, if s is greater than or equal to 0, f of x is e raised to negative x, and 0 otherwise. F of x equal to 0 if x is less than 0. Here, we divide number line into two pieces. So we must consider the CDF in two cases. Case 1. If x is less than 0. Case 1. X is less than 0. If x is less than 0, how do we find the CDF? We know that f of x, the CDF f of x, that's the probability that x is less or equal to x. CDF f of x is the probability that x is less or equal to x, which is the integral from negative infinity to x, f of x dx. Integral from negative infinity to x, f of x dx. Here, since an upper limit contains x, in general, to avoid confusion, we write f of t dt. In general, to avoid confusion, write f of t dt. And here we know that x is less than 0. That means x is somewhere here. If we take integral from net infinity to x, f of x must be 0. In this interval from net infinity to x, f of x must be 0. And a definite integral of 0. A definite integral of 0 is always 0. A definite integral of 0 is always 0. Case 2. S could be here. If S is greater than or equal to 0. In case 2, if S is here, S is greater or equal to 0. F of x is always in the probability that x less or equal to x. Take integral from net infinity to x. F of x dx. And in general, since the upper limit contains x, we need to write f of t dt. Since the upper limit is x, in order to avoid confusion, write f of t dt here. Use different letters. Now, since x here, x is greater than 0. Since s is greater than 0, we will take integral from net infinity to x. When we take integral from net infinity to x, we must consider two integrals. From net infinity to 0, and then from 0 to x. If we take integral from net infinity to x, we must consider two pieces. Integral from net infinity to 0. Integral from 0 to x. When we take integral from net infinity to 0, f of x is 0. When we take integral from 0 to x, when we take integral from 0 to x, f of x is e raised to negative x. So f of t must be e raised to negative t dt. Then take each integral individually. If we take first integral, the definite integral of 0 is always 0. Definite integral of 0 is always 0. Take the second integral. Here we take antiderivative. We get negative e raised to negative t. T varies from 0 to x. If we plug in x, I get negative e raised to negative x. If I plug in 0, e raised to 0 is 1. Then if we simplify the answer, this can be rewritten as 1 minus e raised to negative x. So combine these two pieces together. The CDF f of x equal to 0 if x is less than 0. F of x equal to 0 if x is less than 0. And CDF f of x equal to 1 minus e raised to negative x if x is greater than or equal to 0. For CDF, write in order from left to right. First case, x is less than 0. Second case, s is greater or equal to 0. For CDF, write in order from left to right. First case, x is less than 0. Second case, s is greater than or equal to 0. That's the CDF. That's the final answer. But here, let me say one thing. Sometimes changing variable it may take too much work. So if you won't confuse yourself, using f of x dx, that's okay. You get exactly the same thing. If you won't confuse yourself, using f of x dx is okay. If it's too much work to change x to t, formally we must change x to t. But if you won't confuse yourself, it's okay to use x here. If you won't confuse yourself, it's okay to use x here. Formally we must use t. But if you won't confuse yourself, we can use x here. We can use f of x dx. Formally, we must use t, but if you won't confuse yourself, we can use x. Because using x, I can simply copy the function here. It will save some time. The work is exactly the same. Then take antiderivative, we have e raised to negative x. Evaluate from 0 to x. If we plug in x, it stays the same. If I plug in x for x, the function stays the same. If I plug in 0, I get negative 1. So this is the informal way to write an answer, which is much easier. But formally, we must change x to t. This is informal. This is the informal way to write an answer. But if you won't confuse yourself, that's okay. Next example. Let the PTF of a random variable x be f of x, where f of x is s cubed over 4 if s is between 0 and 2, and f of x is 0 otherwise. Find the CTF of x. If we know the PTF and try to find the CTF, we take antiderivative. If we know the CTF, we try to find PTF, take derivative. If we know the PTF, we try to find the CTF, we take antiderivative. So here we know the PTF, and we try to find the CTF, so we take antiderivative. Here we take antiderivative. First of all, draw the PDF in the number line. A number line is from net infinity to infinity. Here, f of x is s cubed over 4 if s is between 0 and 2. So 0 is here, 2 is here. F of x here is 3 over 4, s cubed over 4. And 0 otherwise. So f of x equal to 0 here. F of x equal to 0 here. In the middle here, x is between 0 and 2. That means what's in the front is x less than or equal to 0. What's in the back here is x greater than or equal to 2. So since we have three pieces, we need to consider three cases. When we take antiderivative, we must consider three cases. Case 1. X is less than or equal to 0. Case 1, x is less than or equal to 0, x is here. F of x, the CTF f of x is probability that x less or equal to x. That's the integral from net infinity to x. Formally, we must write f of t dt. Formally, we need to write f of t dt. But if you won't confuse yourself, and we can make the computation a little easier, we can simply write f of x dx. If you won't confuse yourself, and we can use f of x, that will make the computation much easier. This x and this x, they are not the same thing. Integral from net infinity to x. From net infinity to x, if s is here, from net infinity to x, f of x must be 0. From net infinity to 0 to x, f of x must be 0. So we have integral from net infinity to x, 0 dx. Definite integral of 0 is always 0. Definite integral of 0 is always 0. That's case 1. If s is less than or equal to 0, f of x, the CTF f of x equal to 0. Case 2. Case 2. If s is between 0 and 2. Case 2. If s is between 0 and 2. Case 2. If s is here, between 0 and 2. The CTF f of x is always probability that x less or equal to x, which is the integral from net infinity to x. F of formally is f of t dt, but to make it easier, we write f of x dx. Then from net infinity to x, when we take integral from net infinity to x, we must consider two pieces. When we take integral from net infinity to x, we must consider two pieces. from negative infinity to 0, f of x is 0. From negative infinity to 0, f of x is 0. From 0 to x, f of x is s cubed over 4. From 0 to x, f of x is s cubed over 4 dx. Then take an antiderivative. We know that definite integral of 0 is always 0. Definite integral of 0 is always 0. For the second integral, take an antiderivative. We get x raised to power 4 over 4 over 16. 4 times 4 is 16. Evaluate from 0 to x. If I plug in x, the function stays the same. If I plug in 0, I get 0. And plus 0 in the front. The final answer is x raised to power 4 over 16. So if s is between 0 and 2, the CDF f of x is x to the power 4 over 16. The CDF is x to the power 4 over 16. That's case 2. Case 3, we must consider s is greater or equal to 2. Case 3, we must consider s is greater than or equal to 2. S is greater than or equal to 2. The CDF f of x is always the probability that x less or equal to x, which is the integral from negative infinity to x. Which is the integral from negative infinity to x. F of x dx. Then here, in the third case, if s is greater or equal to 2, in the third case, if s is greater or equal to 2, x is here. In the third case, when s is greater or equal to 2, x is here. When we take integral from negative infinity to x, when we take integral from negative infinity to x, integral from negative infinity to x, we must consider three different pieces. First piece, when s is less than 0, f of x is 0. When s is between 0 and 2, f of x is x cubed over 4. When s is between 2 and x, f of x is 0. We must consider three cases. First case, when s is less than 0, from negative infinity to 0, f of x is 0. So f of x is 0 times dx. Second case, when s is between 0 and 2, when s is between 0 and 2, f of x is x to the power 4, x to the power 3 over 4. So f of x here is x to the power 3 over 4 dx. For the third piece, when s is between 2 and x, f of x is 0. When s is between 2 and x, f of x is 0. Then take antiderivative. We know that definite integral of 0 is 0. Definite integral of 0 is 0. Definite integral of 0 is always 0. What's left is the middle integral. If we take antiderivative from the middle function, I have x raised to the power 4 over 4. Evaluate from 0 to 2. If I plug in 2 to the power 4, if I take antiderivative, I get s to the power 4 over 16. If I plug in 2 to the power 4 is 16. 16 over 16 is 1. If I plug in 0, I get 0. 1 minus 0 is 1. So if x is greater than or equal to 2, the CDF f of x is 1. Then we run 3 cases together. We run 3 cases together from left to right. If x is less or equal to 0, f of x is 0. Case 1, if x is less or equal to 0, f of x is 0. So f of x is 0 if x is less or equal to 0. Case 2, s is between 0 and 2. If s is between 0 and 2, f of x is x to the power 4 over 16. if x is between 0 and 2, f of x, the CDF f of x is x raised to power 4 over 16. So the CDF is x raised to power 4 over 16 if x is between 0 and 2. The third case, from left to right, case 1, case 2, case 3. The third case, s is greater than 2. If s is greater than 2, f of x equal to 1. So f of x equal to 1 if x is greater than or equal to 2. That's the CDF. Next example, let the PDF of a random variable x be f of x, where f of x is 1 plus x if s is between -1 and 0, and f of x equal to 1 minus x if s is between 0 and 1, including 0, not including 1, and 0 otherwise. Find the CDF of x. If we know the PDF and we try to find the CDF, we take an antiderivative. When we are taking antiderivative, first of all, draw the PDF on the number line. When we're taking antiderivative, first of all, draw the PDF on the number line. On the number line, x is from -infinity to infinity. If s is between -1 and 0, if s is between -1 and 0, f of x is 1 minus 1 plus x. If s is between 0 and 1, f of x is 1 minus x. So what we have here is x between -1 and 0. What we have here is x between 0 and 1, including 0. Then 0 otherwise. So f of x is 0 here. In this region, x is less than or equal to -1. In this region, x is less than or equal to -1. In this region here, x is greater than or equal to 1. That's the PDF. We'll put in the number line. Next, try to find the antiderivative. For the CDF. Here we have 4 different pieces. Since we have 4 different pieces, we must consider x in 4 different cases. Since we have 4 different regions, we must consider x in 4 different cases. S may be here, maybe here, maybe here, maybe here. We must consider x in 4 different cases. Case 1, usually work from left to right. Case 1, x is less than or equal to -1. X is less than or equal to -1. That means x somewhere here. -1 is here. If x is less than or equal to -1, x is somewhere here. The CDF f of x is always the probability that x less or equal to x. Probability that x less or equal to x is the integral from -infinity to x. F of x dx. Well, x is from -infinity to x. From -infinity to x. From -infinity to x. F of x must be 0. From -infinity to x, f of x must be 0. Definite integral of 0 is always 0. Definite integral of 0 is always 0. So if x is less than or equal to -1, the CDF f of x is 0. That's case 1. Case 2. Case 2. If x is between -1 and 0. Case 2. If s is between -1 and 0, that means s is here. Case 2, s is here. CDF f of x is always the probability that x less or equal to x. CDF f of x is always probability that x less or equal to x. That's the integral from -infinity to x. F of x dx. From -infinity to x, there are 2 pieces here. From -infinity, when we take integral from -infinity to x, we must consider 2 different integrals. F of x is 0, f of x is 1 plus x. When x is from negative infinity to negative 1, f of x is 0. And then from negative 1 to x, f of x is 1 plus x. From negative 1 to x, f of x is 1 plus x. Then take integrals. The first integral, we know that definite integral of 0 is always 0. So that's 0. Second integral, we take antiderivative. That's x plus x squared over 2. This is always 0. Take antiderivative for this. That's x plus x squared over 2. Then evaluate from negative 1 to x. When we plug in x, the function stays the same. That's x plus x squared over 2. When we plug in negative 1, we have negative 1 plus 1 over 2. In the parentheses, negative 1 plus 1 over 2 is negative 1 over 2. Minus negative 1 over 2 is positive 1 over 2. So f of x is putting descending order, x squared over 2 plus x minus plus a half. In the parentheses, negative 1 plus half is negative half. Negative half is positive half. That's case 2. If s is between negative 1 and 0, the CDF f of x is x squared over 2 plus x plus half. That's case 2. Case 3. X may be between 0 and 1. Case 3. S may be between 0 and 1. In case 3, S is here. Case 3. S is between 0 and 1, including 0, not 1. The CDF f of x is always probability that x less or equal to x. So take integral from negative infinity to x, f of x dx. And from negative infinity to x, in case 3, from negative infinity to x, we need to consider the integral in 3 pieces. First piece, second piece, and the third piece. First piece, take integral from negative infinity to negative 1. If I take integral from negative infinity to negative 1, f of x is 0. Second piece is from negative 1 to 0. Second piece is the integral from negative 1 to 0. If I take integral from negative 1 to 0, f of x is 1 plus x. So f of x is 1 plus x. Third piece, take integral from 0 to x. If I take integral from 0 to x, f of x must be 1 minus x. Then take each integral individually. First integral of 0 is 0. Definite integral of 0 is 0. The second integral here, take an antiderivative. We have x plus s squared over 2. Evaluate from negative 1 to 0. Third integral here. If we take antiderivative, that's x minus x squared over 2. Evaluate from 0 to x. For the first integral, if I plug in 0, I get 0. If I plug in negative 1, I get negative 1 plus half. And negative 1 plus half is negative half. Negative half is positive half. And the first integral is half. The last integral here, if I plug in x, it stays the same. If I plug in 0, I get 0. Then together we have put everything in order. We have negative x squared over 2 plus x plus half. That means if s is between 0 and 1, between 0 and 1, the CDF f of x is negative x squared over 2 plus x plus half. That's case 3. Case 4, s may be here. S may be greater than 1, greater than or equal to 1. Case 4. If s is greater than or equal to 1, then s is here. If s is greater or equal to 1, s is here. The CDF f of x is always probability that x is less or equal to x. Take integral from negative infinity to x. F of x dx. From negative infinity to x. When we take integral from negative infinity to x, we need to consider 4 different pieces of integrals. First piece, second piece, third piece, and the fourth piece. First piece, take integral from negative infinity to negative 1. F of x is 0. I get 0 dx. Second piece, take integral from negative 1 to 0. F of x is 1 plus x. Third piece, x is between 0 and 1. And here f of x is 1 minus x. Third piece, take integral from 0 to 1. Third piece, take integral from 0 to 1. F of x here is 1 minus x. And there's one more piece. Last piece, take integral from 1 to x. Last piece, take integral from 1 to x. When we take integral from 1 to x, f of x is 1. Sorry, here it should be 0. 0 otherwise. F of x should be 0 here. The PDF f of x should be 0 here. The last integral, take integral from 1 to x. F of x is 0. And we know that definite integral of 0 is always 0. Definite integral of 0 is always 0. So we take integral from the middle for these two integrals. For the second integral here, from the previous case, we know that this integral from negative 1 to 0, 1 plus x, this integral is a half. This integral is half. From case 3, we know that this integral is half. What's left is take integral from this one. So first integral is 0, last integral is 0, second integral is half, plus the third integral here. From the third integral, we take antiderivative. Antiderivative of x, of 1 is x. Antiderivative of x is x squared over 2. Evaluate from 0 to 1. If I plug in 1, I get 1 minus half. If I plug in 0, I get 0. So together, 1 minus half is half. Half plus half is 1. 1 minus 0 is 1. That means when s is greater or equal to 1, the CDF f of x is 1. Next, let's put the answer together. Case 1. If x is less or equal to negative 1, the CDF f of x is 0. If x is less or equal to negative 1, the CDF f of x is 0. Second case. If s is between negative 1 and 0, then the CDF f of x is s squared over 2 plus x plus half. If x is between negative 1 and 0. In general, to make it look a little better, we try to line up if. In general, to make it look a little better, try to line up if. First case, if x is less or equal to negative 1. The third case, if s is between 0 and 1, the CDF f of x is negative s squared over 2 plus x plus half. If s is between 0 and 1, last piece, if s is greater or equal to 1, if s is greater than or equal to 1, the CDF f of x equal to 1. If x is greater than or equal to 1, that's the CDF, that's the answer. But now, it doesn't look very simple. How do we check an answer? This expression doesn't look very simple. How do we check an answer? If we try to check the answer, we must check these three properties of CDF. If we try to check the answer, we must check these three properties of CDF. If we want to check the answer, we must check these three properties of CDF. Limit s approach to negative infinity must be 0. The limit when s approach to infinity must be 1. If s is a continuous non-variable, f of x is always continuous. And the derivative of the CDF must be the PDF. We must check these three properties. So let's check these properties. First property, take limit. If I take limit as s approach to negative infinity, what do we get? If we take limit as s approach to negative infinity, what do we get? When s approach to negative infinity means x is very, very small. X is definitely less than negative 1. So CDF f of x equal to 0. And the limit of 0 is 0. If I take limit as s approach to infinity, what do we get? If we take limit as s approach to infinity, that means s is very, very large. If s is very, very large, x must be greater than 1. So we use f of x equal to 1. If s is very, very large, means s is greater than 1. So we use f of x, the CDF f of x equal to 1. This is a constant. Limit of a constant is the constant itself. So limit when s approaches to negative infinity is 0. Limit when s approaches to infinity is 1. It satisfies the first condition. It satisfies the first condition. Now second condition, check that f is continuous. Second condition, check that f is continuous. Second condition, check that the CDF f is continuous. In the function here, we know that polynomial is continuous. It's always continuous. Polynomials is always continuous. Next, let's check the endpoints. If the endpoint between each pieces matches, then the function is continuous. Let's check the endpoints. For the first piece, if I plug in negative 1, since it's a constant function, it's 0. For the second piece, if I plug in negative 1 here, I have negative 1 squared, which is 1 over 2, plus negative 1 plus half. If we plug in negative 1 here, let me write that formally. For negative 1, for the first step, negative 1, take limit from left side and right side. Limit from left side, x is less than negative 1, which is 0. Limit of a constant is a constant itself. S approach negative 1 from right side. That's the limit s approach to negative 1 from right side. When s approach to negative 1 from right side, x is greater than negative 1. We use f of x equal to s squared over 2 plus x plus half. If we plug in negative 1, we have half minus 1 plus half. Half minus 1 plus half is 0. So left side limit equal to the right side limit. The function must be continuous at negative 1. Left side limit equal to right side limit. The function must be continuous at negative 1. F of x is defined at negative 1. So limit exists, it's continuous and negative 1. Next, let's check another endpoint, 0. Take limit from left side and right side. If I take limit from left side, f of x, when x approaches to 0 from left side, x is less than 0. So we use the function f of x equal to s squared over 2 plus x plus half. If I plug in 0, I get half. So left side limit is half. How about right side limit? Take limit from right side. Take limit from right side. Limit from right side means s is greater than 0. If s is greater than 0, we use f of x equal to negative s squared over 2 plus x plus half. Negative s squared over 2 plus x plus half. Then if I plug in 0, I get half. So left side limit equal to the right side limit. Function f of x is defined at 0, and limit exists, so it must be continuous. F of x is continuous at 0. Next, another gap is 1. Take limit from left side, limit from right side. If we take limit as approach to 1 from left side, I have the limit as approach to 1 from left side. When s approach to 1 from left side, f of x is this. Negative s squared over 2 plus x plus half. If I plug in 1, I get negative half plus 1 plus a half, which is 1. If we take limit s approach to 1 from the right side, limit from right side. That's the limit s approach to 1 from right side. Limit s approach to 1 from right side, x is greater or equal to 1, f of x is 1. Left side limit match right side limit. So limit is 1. Limit is 1. And we know that f of 1 is also 1. Limit exists. Limit equal to the limit value equal to the function value. It must be continuous. So it's a shortcut. You can simply plug in negative 1 here, plug in negative 1 here. If the value match, it must be continuous. For 0, you can plug in 0 here, plug in 0 here. It's a shortcut. Plug in 0 here, plug in 0 here. If the value match, the function must be continuous at 0. And same thing here. Plug in 1, plug in 1, plug in 1 to both functions. If the value match, it must be continuous at 1. That's a shortcut to check the answer. So it satisfies the second condition. Here it satisfies the second condition, f of s is continuous. The third condition, if I take derivative from the CDF, I must get a PDF. If I take derivative from the CDF, I must get a PDF. If I take derivative for 0, I get 0. If I take derivative for 0, I get 0. Let's match f of x equal to 0 here. If I take derivative here, I get x plus 1. If I take derivative for the second piece, I get x plus 1, which match the second piece here. For the third piece, if I take derivative, I get negative x plus 1. If I take derivative here, I get negative x plus 1, which match the third piece here. And the last piece, f of x is 1. If I take derivative for 1, I get 0. Let's match the last piece here. So we take derivative for 0. I get 0. Let's match the first piece. Let's match the first piece here. I take derivative for x squared over 2 plus x plus half. I get x plus 1. Let's match the second piece here. On the third piece, if I take derivative for negative x squared over 2 plus x plus half, I get negative x plus 1. Let's match the third pieces here. Let's match the third piece here. For the last piece, f of x is 1. If I take derivative for 1, I get 0. Let's match the last piece here. So that's how we verify the answer. That's how we check the answer. In general, we don't have to check the answer. But if we want to check, that's how we check the answer here. That's how I show you. Value for these three properties. That's how we check the answer. Value for these three properties. Value for these three properties. That's how we check the answer. In general, we don't have to check the answer. That's the final answer. In general, we don't need to check the answer.